eigenvectors of a linear transformation and of a matrix. But before that, before I start eigenvalue eigenvectors, I'll start with some motivation. Okay, so let us look at this question first. So change of basis. So suppose that we have a vector space, let's say V, and let's say it's a finite dimension. So dimension of V is n, and suppose we have a linear operator T on this vector space V. Okay, then we know that if we fix a basis for this vector space, then we can find a matrix for this V, for this T. So with respect to every basis, we can find a matrix representation of this linear transformation. So now the question is, what is the, so if suppose we have two bases, let's say, for this vector space, and if we find matrix representation with respect to these two bases, so I will get two different bases, two different matrices. Then the question is, what is the relation between these two different representation, matrix representation, or what is the relation between matrix of T with respect to one basis and matrix of T with respect to another basis. So let's say if we have two bases, let us call first one as B, where the vectors are denoted by V1 to Vn, and the other one is denoted by B dash, and the vectors are denoted by, let's say, U1 to Un. These are bases, two bases of V. Okay. So the question here is that what is the relation between matrix of T with respect to B and matrix of T with respect to B dash? This is the question. Okay. So this we'll answer first. So to answer this, let us make this observation. Let's say observation 1. So we have two bases, okay, two bases of B. So suppose that I write this one basis in terms of another basis, that I can do, right? Because here these are vectors. They are vectors in V. Here also they are vectors in V. So I will write, let's say, I'll start writing these VIs in terms of these UIs. This I can do because this is a basis and these vectors belong to V. So I can write each of these VI in terms of UI. So let's say, so let us denote this matrix P. So what is this matrix? I will tell you. So the entries of P are denoted by this small Pij. So let P be a matrix such that Vj is equal to summation I equal to 1 to n Pij Ui. So basically what I did here, I have written this Vj. For each j, I have written Vj's in terms of these UIs here. And then whatever, so I can do that because these UIs, they form a basis and these are vectors in V. So I can write these Vj's in terms of UIs, and whatever coordinates I have, I got by doing this, I have stored these coordinates in the matrix as the columns of this matrix. Okay, so the jth column of this P is nothing but the coordinates with respect to coordinates of Vj when you write Vj in terms of Ui. Okay, so this I can do. So this I can do for all j from 1 to n. Okay, now let's say, let us take any element W in V. then what I can do, I can write this W, because these VI's, they are also form a basis. So this is also a basis. So I can write this W. This is any vector. I don't know which one it is. So any vector W. Then is this W I can write in terms of these VI's. So I'll do that. So let's say this I can do as alpha. This, let's say W is written as a linear combination of these VI's in this way for some alpha J's in F. Okay. Then I can write clearly matrix of W with respect to this B. So these VI's, they are coming from the basis B. So the matrix of W with respect to B, I know what it is. It is just a column vector where the entries are these alphas. This we know, we have done this. Okay? How to write a matrix of a vector with respect to a basis. So now what was our W? W was j equal to 1 to n, the summation from j to j equal to 1 to n, alpha j vj. And then I know that what are these vj's? J equal to 1 to n, alpha j. This vj, I know what it is. I can write this vj in terms of this. So what it would be? It would be simply summation I equal to 1 to n pij ui, right? And then what I will do, you can verify that I can interchange the summation here, and it won't affect, and it won't like, it would be the same thing. It won't affect anything. So it would be I equal summation I equal to 1 to n. I can write it in this way. So I'll take the summation with index j inside. Please keep yourself muted. If you're not asking anything, then please keep yourself muted. Okay. So it's the same thing. I've interchanged the summation here, but it won't change anything. But what information it gives you? Now, can you tell me what would be the matrix of W with respect to B dash? Can you tell me this?
Sir, scalar multiplication of column vector.
Yeah, but what it is here? Can you see? Can you tell me from this expression?
P into W
Yeah,
with respect
yeah, you can see here, right? These are the entries of this vector. When you write matrix of W with respect to B dash. So this would be like summation. The first entry would be j equal to 1 to n p1j alpha j and so on. So similarly, the last entry would be j equal to 1 to n pnj alpha j. But what it is? So what is this? This vector. This is the product of P and the matrix of W with respect to B, right? So it's the product of P and these alphas. So for any, so what we can say from this observation, that for any W in V, what we have that matrix of W with respect to B dash is equal to P times matrix of W with respect to B. Let us denote it by equation 1. Okay. So if P is a matrix where the columns are nothing but the coordinates of vectors Vj, when you write it in terms of UIs, then for any W, the matrix of W with respect to B dash is equal to P times the matrix of W with respect to B. This is what we have observed. But there is nothing special. We can just interchange the role of B and B dash. So wherever I have written B, I can write B dash. I can consider B dash. So what I will do in the next thing, I will interchange the role of B and B dash in whatever I did here. Whatever I did here, I will just interchange the role of B and B dash. That means I will write instead of Vj, I'll write Ui, Uj in terms of Vi's, and then I'll do the same thing. If I do the same thing, then what I will get, you can do, and you can see that again, if we interchange, or if we, let's say, if we change the roles of B and B dash in above, then what we get? We get for any, we can say that for any W in V, W matrix of W with respect to B is equal to some matrix, let's say Q times matrix of W with respect to B dash. Okay. So what is this Q? Q is actually like you have you constructed this P. You can also write Q also. What would be Q? The matrix of the columns of Q are nothing but the coordinates of vector uj when you write it in terms of vi's. Okay, similarly you can write this. So any vector w can be written in this way. For any vector w we can write this. So if you now look at equation 1 and 2, so what we can say, so from 1 and 2, what we can say? We can say that, so from 1, matrix of w with respect to b dash is equal to p times matrix of w with respect to b, but that I know what it is. P matrix of w with respect to b is just q times matrix of w with respect to b dash, right? So what we have, that matrix of w with respect to b dash is equal to p times q times matrix of w with respect to b dash, and this is true for all vector w in v. So because we started with any w, so this is true for all w. So what you can say from here?
PQ equals to identity.
Yeah, so this implies, because it is true for all vectors w, so you can say from here that PQ is equal to identity, that is Q is the inverse of P. So this is the first observation we did. Okay. Now let us make another observation. Okay. Observation 2. We know that this we have already seen, that if we have a T linear transformation for this vector space V, then for any V in V, what we have, what would be the matrix of TV with respect to, let's say, B dash? So this we are talking about the same metric, same basis B and V dash. We want to answer this question. Okay. So for this only I am making this observation. So what is this? Can you tell me? We have done this, right? This is equal to matrix of T with respect to B dash and times matrix of V with respect to B dash. Can you recall it? We have done this.
Yes, sir.
Yes.
Yes, sir.
Oh, okay. All right. So now from this, if you apply the observation 1, whatever we observe in observation 1, if you apply on this, then what you can say, so this is for any w, right? For any vector v, this is true. So what you can say from, let's say, from 1, so what was 1? So from 1 we have this, so that any vector w, the matrix of w with respect to basis b is equal to q times matrix of w with respect to b dash, right? So what we can say from here, and similarly from 2 here. So let me write this from 1 and 2. So from 1 I can say, if I apply on this T of V, so what it would be? It would be P. So the left hand side would be P times matrix of T of V with respect to V. This is because of this, because for any vector this is true. So I will, instead of W, I will apply this for T of V, for the vector T of V. Okay. So this would be And again, for this, if I do the same for this matrix of V with respect to B dash, it is P times matrix of V with respect to B. Right? Then again, the left hand side I can write matrix of T of V with respect to B is same as matrix of T, the product of matrix of T with respect to V, B, and matrix of V with respect to B. Right? So since I know that this P is invertible, so I can take the inverse of this. So what it would be, matrix of T with respect to V times matrix of V with respect to B is equal to P inverse matrix of T with respect to B dash times matrix of P times matrix of V with respect to B. So what we can say from here, that matrix of T with respect to B minus P inverse times matrix of T with respect to B dash times P matrix of V with respect to B is equal to 0, and this is true for all vectors V in V. Right? So what you can say from here, that matrix of T with respect to B is equal to P inverse matrix of T with respect to B dash times matrix of P. So this is what is the relation you got from this observation. So matrix of T with respect to B and matrix of T with respect to B dash, they are related via this relation. So this has a name. So do you know what we can say from this? So can we say that this matrix of T with respect to B and matrix of T with respect to B dash are, let's say, from this
Similar.
expression, they are similar?
Similar matrix.
So they are similar matrices. So if we have two bases, and if we have their matrix, if we have matrix representation of a linear transformation with respect to these two bases, then we can say that they are related or they are similar. So these matrices are similar. So the answer to the question which we asked, so the answer of that question is the following: is that there exists. So question was, what is the relation between these two? So the answer is, okay, there exists, they are similar. That means there exists an invertible P, and you also know what is this P matrix, right? This P
Yes,
matrix
sir.
you obtain by writing one basis in terms of another basis. So there exists an invertible matrix P of size n cross n such that matrix of T is similar to matrix of T with respect to B dash via this matrix P. This is the answer. So these two matrices are similar. So before I proceed further, let me just recall for others who do not know what is similar matrices. So what is similar matrix? Let me define this here so that you can recall. Similar matrices. So if suppose we have two matrices of the same size, let's say A and B, of size n cross n over the same field F, then this matrix B is called, or B is said to be similar if similar to A, similar to A if there exists an invertible matrix P such that B is equal to P inverse AP. Okay. So if we have two matrices A and B, then B is similar to A. There exists an invertible matrix that B can be written as this product P inverse AP. And for this we sometimes write this also. We use this notation, this abbreviation we use. So this means B is similar to A. So this means, so let me write this. This is the abbreviation we use. That means B is similar to A. So if you observe, then you can conclude that this similarity, or this is the relation on the set of all matrices of size n cross n. So two matrices are related if they are similar. So this is the relation, this on the set of matrices. Not only relation, it is an equivalence relation on the set of n cross n matrices. So you can say that, or you can observe that. So this is an observation you can make, that this relation, that means the similarity relation, this is an equivalence relation. Equivalence means it's a reflexive, it's symmetric, and it is also transitive. So this is an equivalence relation on the set of n cross n matrices of the same field. Okay. Now you know that if we have an equivalence relation on a set, then so for equivalence relation we can write equivalence classes, right? So do you know what is the equivalence class?
Yes, sir, we can define.
Yeah, what is that?
So class of A is a set of all matrices which is similar to A.
Yeah, so for every matrix A, the class of A is the set of all matrices which are similar to this matrix A. Okay, you are right. So we can write equivalence classes for this equivalence relation. Okay, so what is equivalence class? That also let me just quickly define, or just recall. So recall what is an equivalence class. So if suppose we have an equivalence relation, this is a general statement I am saying here. So if this is an equivalence relation on a set S, and let's say X is any element of S, then the set, let's say this one, E subscript X, is, what is this set? This is the collection of all elements in S which are related to X via this relation. Then this set is called the equivalence class of X. Class of X. Similarly, you can write for other vectors. So for every vector, we can define this equivalence class. So basically, there is a result. So similarly, we can say this we can say for every equivalence relation. So in particular, our interest is to talk about this equivalence relation here, which is defined by similarity matrices, similar matrices. So we can say that if we take any matrix A, then the equivalence class of A is a collection of all matrices which are similar to A. So these equivalence classes, they provides us a partition of the set S. Okay, so there is a result that says that. So let me again recall that. Again recall this result, that if we have a so what is a partition? You know what is a partition? It's a, so if suppose we have a set S, then partition is the, so let's say if we have A1, A2, these are the subsets of S, finite or infinite, we don't care. So let's say these are the subsets of S, such that this AI intersection AJ is empty. That means they are pairwise disjoint for all IJ, and their union, if you take their union, then this forms, this is the, this gives you the complete set S. Okay, so union of all these subsets is equal to S. Then these AIs, they form a partition. So if this is S, then you can say, okay, this A1, A2, A3, and so on, they provides a partition of this S. Okay, so this equivalence relation or equivalence classes, they form a partition of the set S. So the result is that, let me write this as a result just to recall. These are the basic set theory results. Given an equivalence relation, on a set, let's say S, the set of disjoint equivalence classes form a partition of S. That means if you collect only the disjoint classes, then that means for any xy in S, what is the meaning of this? That means for any two elements x and y in S, you can say either the equivalence class of Ex is equal to Ey, or Ex intersection Ey
EX
is
intersection 5.
empty. Yeah. And second is S is the union of all these disjoint equivalence classes. Okay. So now if we talk about equivalence classes of the relation which is defined by similarity matrices, then also we can do this. What is the advantage of equivalence relation? I'll tell you. So it provide, the equivalence classes provides us a disjoint partition of the set S. So this is our set S. Then what it says that, okay, instead of looking at the whole set, you can just focus on these disjoint equivalence classes. Let's say this E1, E2, these are the classes. Let's say X1, X2, X3, and so on. For each, so you can write this as, or you can provide a partition of this set as in this kind of equivalence classes. Now you know that if you take any element in this, let's say Y, in any equivalence class, then this Y, if this belongs to this equivalence class, then you know that Y and X, they are related. Okay, so if you take the equivalence class of Y, then it is the same thing, the same set. If you take any element in these, then it would be the same. It would give, the equivalence class would be the same. So all these elements, all elements in this equivalence classes, in this equivalence class, they are related. Now the question is, okay, they are related. So this relation, this relation is actually gives you a lot of information. So it depends on what is that relation. For example, this similarity relation, this will tell many things about two matrices, how they are, like if they are related, they are similar, then they enjoy some nice properties, same properties. And most the some of the properties are exactly same for all the matrices that are similar. So for example, now if we have this kind of situation where we have a kind of partition of this set S, and in any of this class here, all the all the elements are related. So the question here, okay, if they are related, then can we choose a representative for this class, right? So for each of this class, if two elements belong to the same class, they are related. So instead of saying about the whole class or all the elements belonging to one class, can we say, can we choose an element which is uh, like which acts like a representative of this class. So let's say for this first class, I'll take, let's say, some x1 tilde, then this is some x2 tilde, and so on for each of this class. So now instead of talking about this, I will talk about this representative, and then I will look at the properties of this representative, and then I will say, okay, whatever be the properties of this x1 in this representative, uh, under this equivalence relation, these properties are also enjoyed by the other elements in this. So now the question is how to choose this representative in such a way that it tells us about these properties, or to find the properties of elements in a particular equivalence class. The class is easy. So finding a representative, this is sort of called like a representation of, or you can say like a sort of canonical form for this equivalence class. So can I find if the elements belonging to this, then can I find a representative, or can I find a form of the elements which belong to here, which is like easy in some sense? I'll tell you why, what is the meaning of easy in our case. But this is a general idea that if we have a partition, we have divided in our set into disjoint classes, then the next job is to find a representative for each class, so that that representative will represent the elements of that class. Okay. Okay. So now let's come back to our relation, which is defined by the similar matrices. Now, this is an equivalence relation, so that will also provide us a partition of the set of all n cross n matrices. Okay. Now you can easily check, you can easily see that if we have two similar matrices, let's say A and B, then what can you say about their trace? If B and A are similar matrices, what can you say about their trace? Can you say that the trace of B is same as trace of A, or it is greater than, less than? Is there any relation?
सेम होगा सर.
Same होगा, why?
सर B इक्वल टू P इनवर्स AP हो जाएगा, तो P को इधर लेकर आएंगे तो ये सेम हो जाएगा.
Because trace of AB is equal to trace of BA. That property you are using, right?
Yes, sir.
So trace of B is equal to trace of A. How about the determinant? What can you say about the determinant of B?
Equal, sir.
They are equal? Again,
Yes,
by
sir.
using the determinant property. What can you say about their rank?
Equal.
Equal. So that also you can verify that they have the same rank. Not only this, although we have not introduced these terms yet. Sorry.
Sir, rank A, not determinant A.
Rank.
So rank of B equals
B
to rank
to
of A.
rank A.
Oh, sorry. Yeah. Rank of. Sorry. Yeah. Thank you. Rank of. Right. Now, these are some easy property you can easily check that if A and B are two similar matrices, then they have the same trace, they have the same determinant, and they have the same rank. Not only that, after introducing some other terms, you can say that they have the same characteristic polynomial, they have the same eigenvalues, they have the same minimal polynomials. Although I have not introduced these terms, but let us assume that after maybe today's lecture, you will know what are these terms. So this is just to tell you that they have the same characteristic polynomial. So this is the, let me write, same characteristic polynomial. Characteristic polynomial. They have the same eigenvalues. So this is the set of eigenvalues of B is equal to the set of eigenvalues of A. So that means same eigenvalues. We will introduce these things in today's lecture, hopefully. And let's say they have the same minimal polynomial also. So they have the same. So for the timing, just assume that these terms are there. And once we introduce them, then you can verify that these whatever I'm writing, it makes sense. Same minimum polynomial. All right. So now you can see that if we have two similar matrices, then these properties, these are some of the properties I have listed. These properties are same, exactly same. So now you know that if you have, let's say, now again let me come back to what I was saying. So if we have a set S, this is the set of matrices, then we have like a partition for this, where this is partition into disjoint subclasses. These subclasses are obtained, or these equivalence classes are obtained by defined by this equivalence relation, similarity relation. And we know that if any two elements belong to the same class, then they have the same these at least these many properties. Now, if you, as I was saying, now our job is to find a representative. Now, but if we find a representative which is easy in the sense that it has lot of zeros. If I talk about matrices, if it has lot of zeros, so that I can easily calculate or easily compute these, at least these properties, because they have the same thing. So if I take any two matrices in this equivalence class, then I know that they have the same trace, they have the same determinant, same rank. Any two matrices I take, then they have the same these many properties. So if I, in particular, if I am if I choose a let's say a representative for this class, which is as simple as possible. Simple means, let's say, if I find a diagonal matrix, somehow I can find a representative for this subclass, which is a diagonal. Then you can see that finding its trace, determinant, rank, eigenvalues, characteristic polynomial, everything is very easy for a diagonal matrix, right? So
Yes, sir.
this is what we are trying to do. So the question is, can we choose a representative from each equivalence class which is as simple as possible and provides maximum information of the class elements? This is the question next. This is the next question. Okay, so from this, like, we can impose this question, or let's say we can aim to answer this. So our aim is to, let's say, to choose a representative from each equivalence class which is as simple as possible and provides maximum information about the class elements. Information of the class elements. And in case of similar matrices, again we do the same thing. This is the general question you can ask for any like a partition uh, of the set. But then in case of similar matrices, we ask the same question: can we choose a simple representative which is as simple as possible? And in terms of matrices, simple means the matrix has many zeros, or matrix with most zeros. Okay, so the question for matrices we can ask in this way, that can we find a matrix from each class which has as many zeros as possible. So the best possible we can ask is the diagonal matrix. Can we find a representative for each of these subclass as a diagonal matrix? But this is the aim we are targeting. But whether we can do this or not, that we'll answer. Okay. So this is for matrices. But if suppose I want to ask the similar question for a matrix representation of T. So then what would be the question? The question would be, we know that if I take two bases and if I take their matrix representation, then these two matrices, these two matrix representations, they are similar. So in terms of matrix, what should I in terms of like linear transformation, what should I ask? Equivalently, the same question we can ask. Equivalently, can we choose a basis V of V such that matrix of T with respect to that basis is as simple as possible, right? Because I know that if I take any two bases and their matrix representation, they are similar. So my aim is to find a basis such that the matrix of T is as simple as possible, right? So equivalently, we can ask this question for linear transformation also, like equivalently, can we choose a basis, let's say B of V, such that the matrix of T with respect to this basis is as simple as possible. Okay, this is the question we will answer. We want to answer, and maybe in the next lecture we will answer this question, or maybe next to next lecture we'll answer. Okay, so now you'll see what best we can do. But before that, I need this terminology or this term, invariant subspace. So let me define that first. At any point, if you have any doubt, you can stop me and you can ask. So invariant subspace, what it is? Suppose that we have a vector space V. Assume that we are talking about the finite dimension only, because we are talking about eigenvalue eigenvectors. So we'll restrict ourselves to finite dimension vector space for this chapter. Okay. So suppose that we have a finite dimension vector space and we have a linear operator on this V. Suppose that U is a subspace of V. So this is the subspace. Okay. Then this U is called an invariant subspace. It is called invariant subspace of V under T, invariant under T, if image of T, yeah, T of U belongs to U. That means T of U is in U for all U belong to U. All right. So then this U is called invariant under T, invariant subspace under T. So that means if you take the image of U under T, it belongs to U itself. Then it is called invariant. Now let us quickly look at some examples of invariant subspace. So if suppose we have a vector space and T is a linear operator, then can you tell me quickly some examples of invariant subspace? So for example,
Null space, range space.
Null space, yeah, you can check that null space of T and range space of T for any linear operator on a finite dimensional vector space. Range of T and null of T, they are invariant under T. So they are invariant subspace. Similarly, you can take the trivial subspaces 0 and the vector space V itself. They are also invariant under any T. any operator T on vector space. Let us take one more example. Let us look at this linear transformation from PNR to PNR. So this is the set of all polynomial functions of degree less than equal to n, and D is the differential operator. That means if you take any polynomial here, it goes to its derivative. Okay. Then can you tell me a invariant subspace for this?
All subspaces. Pn
All
itself.
subspace. So all
A
subspaces.
constant subspace.
Constant subspace.
Yes, sir.
Yeah. So
Sir,
basically,
n
you
minus
can
one.
say, yeah, you all are correct. So then you can say that PMR, where m is less than n, this is invariant under this T. Invariant subspace of this PNR under D. Okay, so this way for any subspace, you just check what is the image of that subspace under the given transformation. If it belongs to the same space, same subspace, then
Sir,
you say that it is invariant.
sir,
Sir, why not
equality हो yes sir.
Equal भी होगा, equal
Equals to
trivial
होगा.
होगा. Yes,
Yes, sir.
yes, equal भी होगा. वो तो trivial है. So yeah, you are right. Okay. But why I'm interested in invariant subspaces, why I introduced this, because now you can see, so now let us again start making observations. So we have not defined eigenvalue eigenvectors yet. We are trying to define that. So we are going in that direction, but let us make this observation again. Okay, suppose that we have a invariant subspace under T. Okay, so this is invariant subspace of a vector space under, suppose V is the vector space of finite dimension, U is a subspace which is invariant subspace under linear transformation T or linear operator T. Okay, so this is a subspace, V is a finite dimension, so I can find this U is also finite dimension, so I can I can find a basis for U. So let's say this U1 to UM, where M is less than N be the dimension of V. This is a basis of U. Okay, this is a basis of U. Then I can easily extend this basis of U to a basis of V. Okay, where K plus M is equal to N. Okay, so let's say this is a basis of. So suppose we have an invariant subspace. It's a subspace, so I can take its basis, and I can extend this basis to a basis of the vector space V. Now this is the basis of V, and we have a linear operator. Can you tell me what would be the matrix representation of T with respect to V? So a general idea of this one. So this is the matrix of T with respect to this V. V is this basis. What form it will have? Can you tell me in general? So this is clearly n cross n matrix, but what would be the form of this this matrix T under this T? Tell me this.
So M cross M matrix, block matrix, M cross M.
So you are
This
saying
would be
that
zero
first
matrix.
would be this M cross M, then
Each zero matrix.
then here it would be 0, then
And here is any C matrix.
here, where here at 2-2 position or at 1-2 position?
So B matrix बोल दो और वहाँ C matrix बोल दो.
This is what you are saying. So All of you agree with him that the matrix of T would be of this form, where at one place you will have M cross M. We don't know what would be the entries of this matrix A at one block. What would be what would be the matrix of, what would be the entries of B and what would be the entries of C? We don't know, but what we know is that we will have a zero matrix here, zero matrix of size K cross K, not K cross M, sorry, K cross M. Do you agree with him?
Yes, sir.
Why this is? Because U is invariant,
Invariant.
right? So because of this, so you others can easily verify this. I'm writing this, that the matrix of T with respect to this basis would be of this. Okay, that's fine. So you remember what we are trying to do? We impose this question, right? Can we find a matrix for which class, from each class which has as many zeros as possible? Or equivalently, we are trying to find a basis such that matrix of T is as simple as possible. Simple means it has many zeros. We are trying to see whether we can find a diagonal matrix. If not, then what else we can do? What the next best we can find? This is what we are trying to do. We don't know yet. So, but what we saw is that if we have an invariant subspace, and if we use its basis to construct a basis of the all vector space, then we can somehow create zeros. That is interesting now. It gives us a way to create zeros in the matrix representation of T with respect to some basis. So it gives us some way to find a basis that gives us zeros in its matrix representation, in the matrix representation of T. Now let us make the next observation then. This gives us some hope. So let us do something better than this. That means instead of one U, let's say we have uh, two invariant subspaces, W and U. Suppose these are two invariant subspaces. Okay, subspaces under T. Under T, and such that V is the direct sum of W and U. You know what is the direct sum, right? So suppose that we have two subspaces and V is the direct sum of W and U. If V is the direct sum of W and U, then you know that if you take the union of basis of W and basis of U, then that union will form a basis of V. That you know, right? We have done this because of direct sum. So you can take the union of these two bases. So let's say V is a basis, U1 to UM. This is a basis of U, and then W1 to WK. This is a basis of W. Then if you take their union, this is a basis of V. So let's say this is a basis of U, and they form a basis of W. Okay, and their union is a basis of V. Now, if I look at the matrix of T with respect to this V, then what would be the form of this matrix? Now, can you tell me what would be the form of this?
cross M.
Sir, A
A M cross M, then
zero नीचे
नीचे 0, then
फिर नॉन डायगोनल में जीरो और डायगोनल में मैट्रिक्स.
yeah, so this would be K cross K. You're right. So this is N cross N matrix. So now you can see that using two invariant subspaces, such that their direct sum gives us the whole space, and if we choose our basis as the union of their basis, then with respect to this basis, the matrix representation has many zeros now. At least you can see that they have zeros. So we already know how to find, in theory at least, we know how to find at least a block diagonal matrix. So it is not diagonal, but it is a block diagonal matrix. All right. So what we can say, so this also others can verify. So we have already created many zeros in this matrix. Now we have become greedy and we want to create more zeros. So what is the best you can expect? So instead of 2, if I have 3 invariant subspaces, right? If I have 3 invariant subspaces whose direct sum is equal to V, then, and if I take the union of their basis, it will be a basis of V. And if I look at the matrix of T with respect to that basis, then again it will give more zeros than this second observation. Do you agree with it? Do you agree
Yes,
with
sir.
me? Yeah. So what best we can expect? Now can you tell me what best we can ask or what best we can hope for?
A and B are diagonal.
Yeah, the T of the matrix of T is diagonal, but when, if I want to ask, do it similar way, how should I like do this? How should I achieve that? So the question would be, suppose if V is a direct sum of one-dimensional subspaces, one-dimensional invariant subspaces, right? And then if I take the union of their basis, so their basis would be just one vector. So for any, so let me just write this so that there is no confusion. So now suppose if V is the direct sum of, let's say, W1, W2, and so on up to Wn, where dimension of Wj is equal to 1 for all j. So these are one-dimensional subspaces, and not only that, they are, and these Wj's, they are invariant under T, invariant under T for all j. So these are one-dimensional invariant subspaces under T. Okay. Now these are one-dimensional, so you can write as Wj as the span of some vector. It's a one dimensional. So let's say Vj is the basis of Wj. Okay. Then if you take the union of all these Vi's, that means this construct this basis V1 to Vn. This is a basis of V. Now, if you look at the matrix of T with respect to this basis, then this would be a diagonal matrix. This would be a diagonal matrix, right? Again, others can verify this. So the conclusion, what we can make here, conclusion here is that if we can find one-dimensional subspaces, at least from these we can say if we can find one-dimensional invariant subspaces whose direct sum is equal to V, then from there we can construct a basis such that the matrix of T is a diagonal, and this is the best we can ask for a matrix, right? As a representative of a class. And also you can see from here that the invariant subspaces of dimension 1, they are of particular or they are of special interest, because now you can see that they gives us a way to find this basis. So you can say from here that these invariant subspaces of dimension 1 are of special interest. Okay, and this you will see in the next result that they also gives us a way or a motivation to define eigenvalue eigenvectors. Okay, so let me write this as a result first. So because they are of special interest, so I will write this result first for them, for one-dimensional invariant subspaces. So this is for invariant subspace of dimension 1. So let W be a subspace of V. So, so let me write it in short. So let W be a subspace of V such that dimension of W is equal to 1. Okay. If dimension of W is equal to 1, then we know and assume that W is equal to alpha V, or you can say span of V. So alpha V, where alpha belongs to F. Because it is a one dimensional, so you can write it as a span of V for some V element of V. So V is non-zero vector. Okay. So it's a one. Suppose that we have a one-dimensional subspace. So one-dimensional means it is a span of some vector. So let us call that vector V. Then W is invariant. So this I'm not saying this is invariant. So far we have just talked about one-dimensional subspace. So W is a one-dimensional subspace whose span, which you can write as a span of a vector V, where V is a non-zero vector in the vector space. Then this W is invariant under linear transformation T, under an operator T on V, if and only if T of V is equal to lambda times V for some lambda is in F. F is the underlying field. Okay. So what this result says that if W is a one-dimensional subspace of this form, then this is invariant under any T. So if you fix a T and then you ask whether W is invariant or not, this is invariant under T if this expression is satisfied. That means T of V is equal to lambda times V for some lambda in the field F. So let me quickly go through the proof. So it's a if and only if. So we have to prove both the directions. It's very straightforward proof. So let us look at the first direction, the if direction. Suppose that W is invariant under T. So let W be invariant. So I'm proving the if direction. So let's W be invariant under T. Now what I have to prove? I have to prove that T of V is equal to lambda times V. This is what I have to prove, right? Now I know that this V belongs to W. V belongs to W, right? Because here you see W is of this form. So this vector V clearly belongs to W. So V belongs to W and W is invariant under T. What does it mean? It means that T of V belongs to W. But since T of V belongs to W and W is of this form, yeah, so then you can say that there exists some lambda in F such that T of V is equal to lambda times V. This is very clear because W is of this form here. All the vectors are of this form alpha times V. So I'm calling this scalar lambda. So if direction is very straightforward. Similarly, the only if direction you can prove. So now assume that T of V is equal to lambda times V for some lambda. Now you have to prove that W is invariant under T. Now in order to do that, so conversely, so let me write that. Conversely, suppose that T of V is equal to lambda times V for some lambda in F. Now we have to prove that W is invariant under T. So if I take any W in the subspace W, then I should show that T of W is also in W. Now W belongs to W. That means W is of the form alpha times V for some alpha in F. And now if I take T of W, T is a linear operator, so it is same as alpha times T of W or T of V, right? But then the right hand side would be what? T of V, I know it is lambda times V, so it is alpha lambda times V. But if I call this alpha lambda as, let's say, some other scalar, let's say mu, then what it would be? It says that T of W is equal to mu times V. But what does it mean? It means that T of W belongs to W. And this is true for any vector small w. So this implies that T is W is invariant under T. So what I want to say from this result is that any one-dimensional subspace is invariant under T if this kind of expression is satisfied. That means for a vector V, T of V, non-zero vector V, for any non, in fact you can say that for a non-zero vector V in W, T of V is equal to lambda times V for some lambda, scalar lambda. And this expression, have you seen this kind of expression somewhere? T of V is equal to lambda times V.
Yes, sir, eigenvalues.
Yes.
Yeah, this is how this is.
Eigenvectors.
Yes, eigenvalue, eigenvectors. In the definition of eigenvalue, eigenvectors, you see this kind of thing. So this gives us a motivation now to define eigenvalue, eigenvectors. So let us define first eigen. So we will study eigenvalue, eigenvectors parallelly for linear transformation and matrices. Okay, because and then at one point I will establish a relation between the eigenvalues of T and eigenvalues of matrix of T. You will see that they are same, and therefore we can only focus on the matrices. Okay, but for the timing, for your knowledge, let me define eigenvalues of a linear transformation. So eigenvalue of T, this is what I'm trying to define. Okay, so let V be a vector space over F over the field F. Here F is important to mention, that's why I have written here. And suppose that T is a linear operator on V. Okay, then lambda, a scalar in F, is called an eigenvalue. Is called an eigenvalue. For eigenvalue, I may use this abbreviation. The short form E dot value is an eigenvalue of T if there exists a non-zero vector, let's say V in V, such that T of V is equal to lambda times V. Okay, so if there exists a scalar lambda and a non-zero vector V such that this expression is satisfied, then you say lambda is an eigenvalue of V, and this vector V is called an eigenvector of T with respect to eigenvalue lambda. Okay? So, but before that, let me underline that this is very important here, non-zero vector. Okay? This has to be, because if it is a zero vector, then this expression is satisfied for all lambda, right? This equation is satisfied for all lambda if V is zero. So then there is nothing to talk about this. There is nothing interesting. So we are interested in the non-zero vector V that satisfies this expression. So this vector V is called an eigenvector. For eigenvector, I may use this abbreviation, eigenvector of T with respect to eigenvalue lambda. So whenever you talk about eigenvector, you have to say eigenvector of what? Eigenvector with respect to some lambda. Okay, you have to talk about. And clearly you can see here, if lambda is an eigenvalue, then clearly what you can say that or maybe T is an operator, then you can say that, okay, what is this? Can you say that T minus lambda is also an operator? Lambda is a scalar and I is the identity operator. So this is again an operator,
Yes,
right?
sir.
This is
A
again a
linear.
linear operator on V. So clearly you can see from the way eigenvalues are defined, you can say that V is an eigenvector of T with respect to eigenvalue lambda, if and only if, what can you say? If and only if
V belongs
V
to null
belongs
space of
to,
T minus null space of T
yeah,
minus lambda
T
I.
minus, right. V belongs to, of course, V is non-zero. If and only if V belongs to null space of T minus lambda. Okay. And also for the, just to denote the set of all eigenvalues, we don't know how many eigenvalues there could be, but we collect all the eigenvalues and we put them in a set and we call this set as IIT. This is the notation we'll use. So the set of all eigenvalues of T is denoted by I of T. So this is the notation I will use to denote the eigenvalues of T. Okay. Similarly, we can, so this is the definition of eigenvalues of a linear transformation. But on the same lines, we can talk about eigenvalues of a matrix also. So let me define that also, and then we will move further. So let me define eigenvalues of a matrix also. Eigenvalues of a matrix. So let's say of A, which is n cross n matrix over F. So let A be n cross n matrix over the field F, then a scalar lambda in F is called an eigenvalue. It's called an eigenvalue of A if there exists a non-zero vector, let's say x in this Fn, such that Ax equal to lambda x. So it's very similar to what we have defined for an operator. So if there exists a vector x in Fn such that Ax equal to lambda x, then lambda is called an eigenvalue, and this vector x is called the corresponding eigenvector. X is called an eigenvector of A with respect to eigenvalue lambda. Okay. Similarly, you can, whatever you said for eigenvectors of linear operator. Similarly, you can say that X is an eigenvector of A. The way it is defined, you can clearly say that X is an eigenvector of A with respect to eigenvalue lambda if and only if lambda V belongs to null space of
This X.
A minus, yeah, sorry, X belongs to, yeah, you're right, X belong to null space of A minus lambda I, and of course X has to be non-zero. So this null space of A, so this is if and only if. So you can say from here that any non-zero vector in the null space of A minus lambda I satisfy this expression, and therefore it is an eigenvector corresponding to eigenvalue lambda. So clearly you can see that eigenvectors corresponding to an eigenvalue are, it is not unique. Eigenvector is not unique. So there may be more than one eigenvector corresponding to one eigenvalue. In fact, every scalar multiple of an eigenvector is also an eigenvector corresponding to the same eigenvalue, right? Any scalar multiple, any non-zero scalar multiple, because the vector has to be non-zero. So this null space of A minus lambda I, this is very important for us. This is called the eigenspace. Eigenspace, because every vector, every non-zero vector in this is an eigenvector corresponding to eigenvalue lambda. Is called the eigenspace associated with the eigenvalue lambda. So null of A minus lambda I is an eigenvector, is the eigenspace associated with the eigenvalue lambda. For this we can use this notation, actually E lambda A. Okay. So we can fix some notation for this, so we don't have to write every time this. So E lambda A. This is to denote the eigenspace corresponding to eigenvalue lambda. And again, Ig of A, this will denote the set of eigenvalues. Set of all eigenvalues of A. Now you can see here, let us make this observation. I will write this as an observation here. You can say clearly, if lambda is an eigenvalue, of A, then what can you say about the determinant of this matrix A minus lambda I?
Zero.
0. Why this is 0?
Null space is dimension, matlab more than dimension 1. That
Because ax equal to lambda x and x is non-zero, we take a minus lambda I into x equal to 0, where x is non-zero. Means ax equal to 0 has a non-trivial solution.
Yes.
From
so
here,
therefore, yeah. So from there also you can conclude that x is a non-trivial solution of this system A minus lambda I x equal to 0, and therefore determinant is 0. Is the converse also true? If the determinant of A minus lambda I equal to 0 for any lambda, then can you say that lambda is an eigenvalue of A?
yes.
So
Yes,
the
sir.
so the converse is also true. So you can say that lambda is an eigenvalue of A if and only if determinant of A minus lambda I equal to 0. Now determinant of A minus lambda I, if you write, then this is a polynomial of degree at most n. If A is of size n cross n, then determinant of A minus lambda I is a polynomial of degree at most n. And you can see from here that these eigenvalues are nothing but the roots of this polynomial, right? Because determinant of this is 0. So that means they are the roots. So eigenvalues are nothing but roots of this polynomial, determinant of A minus lambda I. Therefore, this polynomial is called as a characteristic polynomial of A. So basically, these eigenvalues are also known as characteristic values. So in some books, you will see the characteristic value. They use this term characteristic values in place of eigenvalues. So therefore, this polynomial is called characteristic polynomial. So the polynomial let's say PAZ is equal to determinant of A minus Zi or Zi minus A, whatever you write, Zi minus A, let's say, is called the characteristic polynomial of A. Okay? And the equation PAZ equal to 0, this is called the characteristic equation. That means determinant of Zi minus A equal to 0, this is called the characteristic equation of A. So clearly you can see from here that the eigenvalues of A are nothing but the roots of the characteristic polynomial of A, or you can say the solution of this characteristic equation. So the eigenvalues of A are nothing but the roots of the characteristic polynomial. Fine. So with this we have defined eigenvalue eigenvectors, and we have also set some terminology which will be useful for us in order to talk more about these eigenvalue eigenvectors. Clearly now, since we have defined eigenvalue eigenvectors of a linear operator, and we have also talked about eigenvalue eigenvectors, at least we have defined eigenvalue eigenvectors of a matrix. Okay. So now the next question is, so for a linear operator, we can talk about just eigenvalue eigenvectors, and if I take its matrix representation with respect to any basis, then if I fix a basis, then I can talk about its matrix representation. So I have a T, and I also have matrix of T. So for T, I know eigenvalue eigenvectors, and for matrix of T, which is a matrix, I also know eigenvalue eigenvectors. Now the question is, what is the relation between the eigenvalues of T and eigenvalues of matrix of T with respect to some basis? This is the question. And the answer is that the eigenvalues of T and eigenvalues of matrix of T with respect to basis, they are same. So they have the same set of eigenvalues. And this result is independent of the choice of basis. So even if you change the basis, the set of eigenvalues will not change. Okay, so we will prove maybe in the next class that if we have a vector space finite dimension, let's say, and if we fix a basis B of the vector space, and let's say T is a linear operator on V, then eigenvalues of T are same as eigenvalues of matrix of T with respect to this B. Okay, and this is free of or this set of eigenvalues of T is independent of the choice of B. Why this is? Because you can check that similar matrices have the same characteristic polynomial, and hence they have the same eigenvalues, because eigenvalues are nothing but the roots of the characteristic polynomial. So you can clearly see, so I can give you this as an exercise, that similar matrices have the same characteristic polynomial and hence same eigenvalues. Okay, this you can verify, and using this we will conclude that set of eigenvalues of T are same as set of eigenvalues of matrix of T with respect to any basis. So it doesn't matter which basis you are choosing, the set of eigenvalues would be same. This we will prove in the next class, and we can stop here. We still got 5 minutes, so I want to make a comment here. So I received one or two emails from you saying that you were not able to give the quiz because you were having some like you were sick or you were having some other problem. that's fine. I mean, I cannot I cannot consider each of these requests, because otherwise I won't be able to conduct quiz anytime. So it's always somebody will be having some issue. So we cannot postpone the quiz on a particular request. But what we can do is that we will see what is the other solution for that student. So for example, we have already conducted 2 quizzes. So we have already conducted 2 quizzes.